Now that we're getting to the coding sections, I need to stress to absolutely use the GitHub repository associated with this course. If you come to the GitHub repo and you scroll down and you click the lesson that we're on, right now we're on lesson 2, Welcome to Remix, Simple Storage. If you click on it, it'll give you a ton of timestamps and other helpful links associated with this lesson. Additionally, the biggest piece is that all the code will be available right underneath the lesson title. This will have all the code that we're going to be working with, as well as some more additional information on how to work with the code. Please, when asking questions and entering in discussions, though, please ask your questions in the full Blockchain Solidity course repository. Thank you. And if we're at the top of the repository and we scroll down, we have this resources for this course section, which brings us to the GitHub discussions, which you can ask questions in the GitHub discussion section of this course. Additionally, on Stack Exchange Ethereum or Stack Overflow. I'll talk a little bit about how to format questions and ask questions the best way so that you have the highest chance of getting a good answer in a later lesson. I highly recommend you pause and make accounts for Stack Exchange Ethereum, Stack Overflow, and GitHub right now if you haven't already. Links to them, of course, can be found in our GitHub repository. Typically, for each coding section, I'll start it off by giving a quick overview of the code of what we're going to be working with and what we're going to be building towards, since everything that we're doing is going to be project-based, and that's how we're going to learn. For our first one in Remix, though, we're going to skip over that because there's a lot of stuff to get used to. Now, I highly recommend that as I'm coding this and as I'm doing all this in Remix, you follow along with me and you code along with me. Remember, you can change my speed if I'm coding too fast or if I'm coding too slow. To start, we're going to jump into a tool called Remix. If you're unsure how to get there, there's a link to Remix in our GitHub repository. This is where we're going to be writing all of our code. So welcome to the Remix IDE, or Integrated Development Environment. This is where we're going to learn how to code and interact with our smart contracts. If you want, you can go ahead and accept to help out Remix. If you've never been here before, it'll give you a quick walkthrough of some of the tools that Remix actually has. We're going to skip over them for now because I'm going to explain everything that's going on. Remix is such a powerful tool because it has a lot of features that allow us to really see and interact with our smart contracts. Eventually, we're going to move off of Remix actually to a local development environment. However, Remix is absolutely fantastic for learning the fundamentals of Solidity, and I highly recommend everybody start with Remix when they're getting started. When you come to the Remix IDE, there's a whole lot of different things that are popping out to us. There's a lot of different plugins as well. Since we're going to be working with Solidity, which is going to be the language that we're using to develop our smart contracts, we can go ahead and get started by clicking the Solidity plugin. And a couple of other tools will show up on the side. Even if you don't click the Solidity plugin, you'll still be able to code Solidity smart contracts. The left-hand side is where we're going to start to actually interact with things. The button on the topmost of the left is our files or our Explorer directories. Remix comes boilerplated with some different contracts, some different scripts, some different tests, and different dependencies. We are going to minimize this a little bit. So if you want to go ahead and right click and delete some of these folders, other than the contracts folders, feel free to do so. Or if you kind of like them there, feel free to leave them as well. We're going to leave our contracts folder and we're going to delete the different files inside of it just so that we can start from a blank slate. Most projects come with something known as a README. Usually it's a readme.md, which usually explains how to actually work with code. But for our purposes, we're going to delete this as well, and you can just follow along with me. Now we have a blank Remix setup. Click on the contracts folder and click the little page icon to create a new file. A little box will pop up and you can start typing text into it. We're going to type in simple storage.sol. .sol tells our compilers that this is going to be a Solidity file and that we're going to code Solidity in this. Solidity is the primary coding language of smart contracts. There are a few other smart contract languages as well, but Solidity by far is the most dominant smart contract coding language out there. And now we have a simple storage.sol contract on the right that we can actually start coding our Solidity with. So let's start coding some Solidity. Now, if you click on this button right below the files button that looks like the Solidity logo, you'll see a bunch of stuff pop up in here. These are different parameters for us to actually compile our Solidity code so that we can run it. So the first thing that you're going to need in any Solidity smart contract is going to be the version of Solidity that you're going to use. And this should always be at the top of your Solidity code. Solidity is a constantly changing language and a constantly updating language because it's relatively new compared to other languages. We need to tell our code, hey, this is the version that I want you to use. We can add the Solidity version by doing pragma Solidity and then the version that we want to use. If we want to choose a very specific version, we could say 0.8.7. The most current version to date is 0.8.12, but getting used to different versions of Solidity is good practice. And different versions of Solidity are considered more stable than others. 0.8.7 is one of those versions that is considered more stable. These double slashes here are what's known as a comment. They're places where you can type stuff that won't actually get executed and won't get compiled and isn't really considered part of your code. For example, I could write, hello all, I'm Patrick. And if we were going to run this code, this part of my code would get completely ignored. So this double backslash is how we do what's called comments. And as we're coding and as we're building our projects, be sure to use this comments tool to your advantage. Every time you write a new function or you learn something that you didn't understand or you learn something new that you want to remember, put it in a comment in your code. You're going to be most effective at taking notes in this course by making them comments in your code and then saving your code so you can refer back to it later. So leave comments in your code, leave notes in your code, and that'll be one of the best ways for you to understand what you're coding when you want to refer back to it later. Now, when it comes to the versions of Solidity, there's actually a few different ways we can actually write it. We can say we want to use only 0.8.7, and this is how we would write that. But maybe we're okay if we use a more new version of Solidity than 0.8.7. To tell our code that we're okay with a more new version, we can put a little caret here. And this is how we tell Solidity, hey, any version of 0.8.7 and above is okay for this contract. This means 0.8.8 would work, 0.8.9, 0.8.10, etc. But if we wanted to use just 0.8.7, we would type it like that. If we want to use Solidity versions between a specific range, we could do something like this. We could say we want our Solidity version greater than or equal to 0.8.7, but less than 0.9.0. This means that any compiler between 0.8.7 and 0.9.0 would work. This means 0.8.8 would work, 0.8.9 would work, 0.8.10 would work, but 0.9.0 would not work because it is not strictly less than 0.9.0. 0.9.1 would also not work. To keep things simple for us, we're going to use 0.8.8. And every line of Solidity that's completed, every completed section needs to end with one of these semicolons. This is how you tell Solidity it's the end of the line. Also, at the top of your code, you're always going to want to put what's called an SPDX license identifier. This is optional, but some compilers will flag you a warning that you don't have one. This is to make licensing and sharing code a lot easier. We have a link to more about how licenses work in the section of this lesson in our GitHub repository. To do an SPDX license identifier, we just say SPDX license identifier, and we're going to choose MIT. The MIT license is one of the least restrictive licenses out there, so we use the MIT license for most of our code samples. Once you have a version, and once you have just this much written, we can actually go ahead right to our compiler tab and scroll down and hit compile. That little turn thing will go, and in a minute, we'll see this contract is attempted to be compiled. Since we actually don't have a contract, we see no contract compiled yet, but we see the compiler automatically switched to 0.8.8. Compiling our code means taking our more human readable code like pragma Solidity and transforming it into computer code or very specific instructions for the computer to use. We'll go over what a lot of this machine level code or this computer level code is doing in a later section. If you're using a Mac, you can also hit Command S and it'll run the compiler for you as well. On Windows, it might be Control S. We can actually choose the compiler version that we want to use. However, if we tell in our code to specifically use 0.8.8 and we hit the compile button, it'll automatically switch to 0.8.8. However, if we use the caret thing, we could specifically say, hey, we want 0.8.10. We could hit compile and it'll compile with 0.8.10. Because again, remember, the caret says we want to use at least 0.8.8 all the way up to the latest version of 0.8. For now, let's stay on 0.8.8. The next thing that we're going to do in our code is define our contract. And to get a full screen view, you can go ahead and hit the compiler button to get rid of it there. To start defining our contract, we're going to go ahead and write the word contract. This tells Solidity that the next pieces of code is going to be a contract. Contract is a key word in Solidity, and it tells our compiler that the next section of this code is going to define a contract. You can think of a contract similar to a class in any object-oriented programming like Java or JavaScript. Let's go ahead and give our contract a name here. We're going to call ours simple storage. And then we add this little open and close curly brackets. Everything inside this open and close curly brackets is going to be the contents of this contract simple storage. Now, if we go ahead and hit Command S or Control S, we can see this little green check mark show up. And if you don't, you can always go back to the compiler tab, scroll down and hit compile and see the little green check mark. That little green check mark means that our code is compiling successfully and we don't have any errors. We could hypothetically deploy this contract right now and it would be a valid contract. So congratulations on writing your first contract. Now Solidity has multiple different types or primitive data types. And if you go to the Solidity documentation, which again is in our GitHub repository, you can read more and learn more about the different types that are in here. The four most basic types are going to be Boolean, uint, int, and an address, or bytes, which is a lower level type, which we'll talk about a little bit later. A Boolean defines some type of true false. A uint is going to be an unsigned integer, which means it's going to be a whole number that isn't positive or negative, it's just positive. We have an integer, which is going to be a positive or negative whole number. And then we have an address, which is going to be an address, like what we see in our MetaMask here. There are some other types as well that you'll learn later on. The reason that we have these types is we use them to define what different variables are. Variables are basically holders for different values. For example, we could create a variable called has favorite number to represent if somebody has a favorite number. And we would put this bool keyword before has favorite number to say, okay, we have a variable called has favorite number and it's of type Boolean. So this has favorite number is going to represent a true or a false. To set its value, we could say has favorite number equals true. Now has favorite number is going to be true. We could also say has favorite number equals false. So this Boolean has favorite number is now going to be false. For uints, we could say uint favorite number equals and then set a number 1, 2, 3. This means that our favorite number is going to be 1, 2, 3. Uint is special because we can actually specify how many bits we want to allocate to this number. Bits and bytes are pretty fundamental pieces of information for computer science. We're not going to go over it here. However, there's a fantastic video in the GitHub repository that explains it more. Basically, it's how much storage or memory to allocate to this number. How big can it get? If we say a uint 8, it can have 8 bits all the way up to uint 256. If you don't specify how big it is, it automatically defaults to uint 256. Oftentimes, it's better when writing our code to be very explicit. So usually you'll see me just do uint 256 to represent a uint 256. We could also do an int favorite number equals 1, 2, 3, or an int 256. I'm just going to go ahead and add this Boolean back here. We're going to change this back to uint 256. And let's change our favorite number to 5 here. We could also do something called strings. String favorite number in text equals 5. Strings represent basically words, and you can represent them by putting them in these quotes. It's going to be some word or phrase or really just kind of any combination of keystrokes in here. Our ints can be positive or negative. So we could say -5 or +5. Both are going to be valid ints. We can also do address. My address equals, and grab our address right from MetaMask and paste it in. You'll notice that we end all of these lines of code with these semicolon. We can also have bytes objects or a bytes 32, again, representing how many bytes we want them to be. And this says that we have called favorite bytes, and we're just going to set it equal to cat. So strings are actually really interesting because strings are secretly just bytes objects, but only for text. So cat is actually a string, but can automatically get converted into one of these bytes object. Bytes objects typically look like 0x and then some random letters and numbers that represent the bytes object. But cat can automatically get converted down to bytes. We'll talk about bytes more in coming sessions. You could also do bytes 2, bytes 3, bytes 5, bytes 22. You get the picture. For our uints and our int256, the lowest we can go is 8 bits because 8 bits is a byte, and we can go up by steps of 8. So we can do 8, 16, 32, etc., all the way to 256. For example, down here, we can't do bytes 64. And if we go ahead and try to compile this, we get a little red thing here. And if we scroll down, we get a declaration error, identifier not found or not unique, byte 64, favorite bytes equals cats. And we even get a little red warning sign here in our remix. This is remix telling us there's something wrong with this line. So we can switch it back to byte 32, since bytes 32 is the maximum size that a bytes can be. You could also do just a bytes object, which means it can have any size. But we typically want to be explicit, and we're going to stick with bytes 32 for now. If you want to learn more about the different types and how to use them and all the different features with them, be sure to check out the Solidity documentation. For now, for our simple storage, let's say we only want to store numbers. So let's go ahead and delete everything except for the favorite number section. Now in Solidity, if I do this and I remove the equals 5, this favorite number actually does get set to a default value. The default value for Solidity is going to be whatever the null value is, which in Solidity's case is 0. So saying uint256 favorite number is going to be the same as saying uint256 favorite number equals 0, since it gets initialized to 0. So for now, let's not initialize it to anything so that favorite number will automatically start off as 0. Now, if you get confused as you're coding along and you're following along with me, be sure to write comments in your code so you know what's going on. So maybe for example, a great comment here would be this gets initialized to 0. And then if that's even confusing you, you could say this means that this section is a comment. Now let's go ahead and create a function. Functions or methods are self-contained modules that will execute some specific set of instructions for us when we call it. If you're familiar with Java or Python or JavaScript or anything like that, functions work the exact same way. Functions get identified by the keyword function. Let's create a function called store that will change the value of favorite number to some new value. And the number that we're going to change it to is going to be variables that are passed to our store function here. So we're going to allow our store function to take a variable of type uint256 and we'll call it underscore favorite number. We'll make this a public function, which we'll get to in a minute. And all we're going to do is we're going to set favorite number equal to whatever variable that we just passed. So now we have this function called store that it takes some parameter that we're going to give it, and it sets this favorite number variable equal to whatever number that we give this function. Now to see this actually in action, let's deploy this to an even faker blockchain than a testnet. We're going to actually deploy this to a local network or a JavaScript VM. And first, before we can even do that, let's just make sure that it's compiling correctly. Looks like we have a green check mark, which is good. And we'll come down to this button here, which is our Deploy and Run Transactions tab. Our Deploy and Run Transactions tab has a ton of different configuration pieces for actually deploying this contract. First, we want to make sure we are on the JavaScript VM London piece here. JavaScript VM means we're going to be deploying to a fake local JavaScript VM. The JavaScript VM is a fake local blockchain where we can simulate transactions really quickly without having to wait for them to go through on a testnet. Don't worry about the London versus Berlin piece here for now. Injected Web3 and Web3 provider we'll talk about in a little bit. We also have this account section here. When we run on our fake JavaScript VM, we're given a whole bunch of fake accounts from where to deploy from. And we're given 100 ETH for each one of these fake accounts. You can kind of think of it similar to our MetaMask account in MetaMask. Except for the difference here is that this is this fake JavaScript VM Ethereum that we're given. For our transactions, including deploying contracts, we're actually given a gas limit. There's also values we can send and we can choose our contracts. Right now, we only have one contract, simple storage, so that's going to be the one that we're going to deploy. So on the left-hand side, to deploy this to our fake JavaScript VM, we're going to go ahead and hit the deploy button. And if we scroll all the way down to the bottom now, we can see a contract was deployed. It says simple storage at X blah, 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 blah. And we see this orange button store with kind of this gray text uint256 underscore favorite number. On our fake local blockchain, we're actually given an address. Every single smart contract, it has an address, just like how our wallets have an address. So if we hit this copy button here and we put it into a comment, we make this a little bit bigger, we can see that the address of this contract that we just deployed is located at this address. Additionally, if you pull up the slider over here, you'll be able to see this little green check mark with all this information about this deployment. And you can hit the little drop down and see a whole lot more information about this. Something you might notice is you'll see some familiar keywords like status, transaction hash, from, to, gas, etc. When we deploy a contract, it's actually the same as sending a transaction. Remember, anytime we do anything on the blockchain, we modify any value, we are sending a transaction. So deploying a contract is modifying the blockchain to have this contract. It's modifying the state of the blockchain. And if we had sent this on a Rinkeby or a Coven or a mainnet network, we would have had to spend the gas to actually deploy this contract. And this is the simulation of how much gas and the transaction hash and from and to and all this other stuff about our transaction had we actually deployed it to a real network. But since it's JavaScript VM, it's all fake information. Now we have this big orange button store. This big orange button resembles the store function that we just created. So if we add some number into this store like 123 and we hit the store button, we actually call this store button and we actually execute a transaction on our fake JavaScript blockchain to store the number 123 for favorite number. And if we scroll all the way up to our account now, you'll see that we have a little bit less ether in our fake account. This is because we spent the gas to actually call this contract. And if we pull up this bottom bit here, and I call this with 5, I call store, you'll see it flash for a quick second. We sent another transaction to store the value 5 in our favorite number. Now, the question you might be having is, that's really cool, Patrick, but I can't see what favorite number actually is. How do I know that those transactions are actually going through? Well, right now, the visibility of our favorite number is set to private, so we actually can't see it. And we'll talk about visibility in just a second. To make it so that we can see it, we'll change our favorite number's visibility to public. So let's go ahead, we'll recompile. We'll go back to the deploy tab. We'll click the little X here, which is to say, let's get rid of this contract. And it just gets rid of it from our window here. It doesn't actually get rid of it from the blockchain because, again, they're immutable. Well, kind of immutable, since, again, this is kind of a fake simulated chain. But we go ahead and compile, and now we hit deploy again. And if we scroll down, our new contract will now have 2 buttons. One is the orange button for store, but now we have a new favorite button. This button represents this public variable favorite number, and it resembles a function saying, hey, show me what favorite number is. So if I were to click this favorite number button, what do you think will show up? Well, do you remember what this gets initialized to? Well, let's click it now. We do indeed see that 0 shows up. We see that this is a uint256 and the value stored in it is 0. Now, if I were to change that number to 5 by calling the store function and now hitting favorite number, we do indeed see favorite number gets updated to 5. Functions and variables can have one of 4 visibility specifiers. We have public, private, external, and internal. Public is visible externally and internally, meaning anybody who interacts with this contract or sees this contract can see what's stored in this favorite number function. You'll see here in the Solidity documentation, it says it creates a getter function for the storage/state variables. When we add this keyword public to favorite number, what we're actually doing is we're creating what's called a getter function for favorite number. We're basically creating a function that says to return the value of favorite number. And that's why this blue button pops up, because this blue button is a function that says, hey, return the value of favorite number. Private means only this specific contract can call this function. Now for storage, it doesn't mean only this contract can read what's stored here. And we'll get into that a little bit later, but private means this is the only contract that can call the favorite number function. Private functions are only visible to the current contract. External functions are only visible externally, meaning somebody outside this contract can call this function. And then internal means that only this contract and its children contract can actually read it. But we'll get into that a little bit later too. So oddly enough, variables are just function calls. Now, the reason that we didn't see favorite number show up on the left-hand side when we first deployed this without the public keyword, when we don't give a visibility specifier to functions or variables, they automatically get deployed as internal. And as we know, internal functions and variables can only be called by this specific contract or derived contracts, which again, we'll get into later. So let's just keep it public for now. The reason that we're prefixing our parameter here with an underscore is a way to tell us, hey, this variable here is different from the favorite number global. There's some different naming conventions that are used for parameters. And as we get later into the course, we'll understand more and more of what good names for parameters are. Every time we call this store function and we change the value here, we're actually sending a transaction, because remember, every single time we change the state of the blockchain, we do it in a transaction, and we can see all the details here. If you go over to the transaction details in the logging area of your remix, you can actually scroll down and you can see the transaction cost in units of gas. You'll see a number something around this, and you'll notice it's more than that 21,000 number from sending Ethereum. That's because we're doing something more computationally expensive. We're actually storing a number over here. Now, what do you think will happen if we do more inside of this store function as well? So instead of just storing this number, maybe what else we do is we will store the number here, and then we'll update our favorite number. We'll say favorite number equals favorite number plus 1. Since we're doing more stuff now, we should see this store function actually become more expensive. So let's go ahead and recompile. We'll delete this. We'll redeploy. We now have a new contract. We'll store 5 again. Now, if we look in the details of this transaction and we scroll down to execution costs, we do indeed see the amount of gas has greatly increased. And that's because we're doing more things. This store function is now more computationally expensive. And like I said, each blockchain has a little different way of how they actually calculate gas, but the easiest way to think about it is the more stuff you do, the more expensive that transaction is going to cost. So let's go ahead and delete this line to continue our example. Now let's talk about scope for a second. Our favorite number is basically in something called the global scope, meaning anything inside of these brackets can access this favorite number variable. But what if I did something like this? What if I made a uint256 called test var and I set it equal to 5? And then I created a new function called something. We'll have it take no parameters and be public. Could I access the test var and then change it to something like 6? Can we do that? Well, let's go ahead and see what happens when we try to compile this. We actually run into an error. We get expected primary expression right here. Oh, well, that's because I have the double question mark. Let's try it now. We get undeclared identifier. Our something function doesn't know about this test var. When you create variables, they only can be viewed in the scope of where they are. Now, if that's a little confusing, just look for the curly brackets. These two curly brackets encompass this whole section here, right? The opening one is up here, the closing one is down here. So if I create a variable directly inside of these curly brackets, that means everything in here can access it. However, test var was created inside of these curly brackets, which means that only stuff inside of these curly brackets can access test var. Since our function something isn't inside of store, our something function won't know about test var. So that's how scope works. You want to look to see if your variable that you created is inside of these curly brackets, and that's how you can know if other functions can work with them. So this is why this fails. Now, like what we saw in the documentation, when we add this public variable to favorite number, we're secretly adding a function that just returns this favorite number. We can also add our own function that also returns the favorite number to resemble the function that's getting created in the backend. So we could say function, we call it retrieve, and we make it a public view, and we'll say it returns a uint256. I'll explain what that means in just a second. And we'll say return favorite number. Now I'm going to hit Command S, which again, I'm going to do that a lot throughout this section. But just remember that that's equivalent to me going to the Compile tab and hitting Compile. Now, if we go to the Deploy tab, delete our last one, deploy a new one, we now have a retrieve function, which is going to return the exact same thing that our favorite number is going to return. Again, if we update this to 5, call favorite number, and then retrieve, they both now return 5. Now, as you can see here, these two functions are blue, but this function is orange. What's the difference? Why do these have these different colors? Well, the key lies in this view keyword here. There are actually two keywords in Solidity that notate a function that doesn't actually have to spend gas to run. And those keywords are view and pure. Oh, and let's also get rid of this variable up here. A function that is a view function means we're just going to read state from this contract. We're just going to read something off of this contract. For example, our retrieve function right now is just reading what favorite number is. A view function disallows any modification of state. So you can't update the blockchain at all with a view function. Pure functions also disallow any modification of state. So we couldn't update our favorite number. Not only that, but they also disallow reading from the blockchain. So we couldn't read favorite number either. Instead, what you might do with a pure function is maybe something like function add public pure 1 plus 1 or return 1 plus 1. This would be returns UN256. Maybe something like this. Maybe there's some math you want to use over and over again. Maybe there's some specific algorithm that you want to implement that doesn't actually need to read any storage, etc. Now, if we call a view function or a pure function by itself, we actually don't need to spend any gas since we're just reading from the blockchain. Remember, we only spend gas, we only make a transaction if we modify the blockchain state. So you'll notice in our little console down here that if I call retrieve, this call thing comes up. However, it looks different than when we call the store function. When we call the store function, we get this little check mark, we get a hash. We don't get the little check mark and we don't get a hash with the calls. That's because clicking these blue buttons doesn't make a transaction. This is saying, hey, we're just going to read off chain. We're just going to read this value. However, if you look in the details of this call, there's this execution cost bit here. So what's going on? Well, we can read this part right here. Cost only applies when called by contract. If we do have a function that calls retrieve, if there's a function that is updating state that calls a view or a pure function, that's the only time it'll cost gas. So for example, if our store function, which is not a view function, were to call retrieve at some point, then we'd have to pay the cost of the retrieve because reading from the blockchain costs this computation and costs gas. Calling view functions is free unless you're calling it inside of a function that costs gas, in which case it will cost gas. So if we leave it here, we delete this, we recompile, we redeploy, we hit favorite number, retrieve, they both still cost nothing. But if we store 8 in here, we can see our execution cost has gone up from what it was without retrieve, which we can go ahead, we can compile. I hit Command S to compile here. We can deploy. Let's go ahead and store again. We'll click on that transaction. We can see that it's much cheaper without that retrieve function in there. And again, our favorite number variable, as long as it has this public visibility, it also is counted as a view function that returns a uint256. The returns keyword means what is this function going to give us after we call it. So we say this function is going to give us, this function is going to return a uint256. When we call retrieve, it's going to return or give us a uint256. This is the result of calling the function. This 6 is the result of calling our retrieve function. Now, our contract is good as it is. It allows us to store a single favorite number. But what if we want to store a range of favorite numbers? Or maybe we want to store a whole bunch of different people who have different favorite numbers. Well, how do we do that? There are several different ways that we could approach this. One of the ways we could start approaching this is by creating what's called a struct of people. Or we could create a new type in our Solidity. We can create a people object that holds both someone's name and their favorite number. To do that, we say struct people uint256 favorite number and a string name. Now we've created a new type called people, kind of like uint256 or Boolean or string. Now we have a people type that we can use. Now, similar to how we created a uint256 public favorite number, we could do the exact same thing, but with a people. We could say people, public, we can call this person, and we can create a new people and assign it to this variable person. So we'll say equals people public person equals, and we'll add parentheses here to signify we're creating a new person. And since we made this a struct, we add little curly brackets here to let Solidity know that we're going to be grabbing from these struct variables. We'll say favorite number is going to be 2, and the name is going to be Patrick, semicolon. And then we can hit Control S, or we can go ahead and compile. Now, if we go ahead and deploy this, we now have a new person. Since this, again, is a public variable, it has a getter function called person. And if we click person, we see our new object. The favorite number is 2, and then the name is Patrick. You see this 0 and this 1 because these are showing the index of the different variables. For those of you new to computer science, typically in computer science, lists start with the number 0. So at our 0th index, we have a uint256 called favorite number, which is saved at 2. And then at index 1, we have a string, which stands for the name of Patrick. Whenever you have a list of variables inside of an object in Solidity, they get automatically indexed. So favorite number gets indexed to 0, and name gets indexed to 1. Interestingly enough, if you have a whole bunch of variables inside your contract, like we have public favorite number, this favorite number actually technically is getting indexed at the 0th storage slot. And if we were to make another one of these, maybe uint256 public brother's favorite number, this would technically be indexed at the 1st slot. And then if we were to make one more, maybe sister's favorite number, this would be indexed at the 2nd slot. So favorite number at 0, this at 1, and this at 2. But we'll learn more about that much later in the course. Similarly, favorite number is indexed at 0, name is indexed at 1. Now what we have is great, but if we want a whole lot of people, are we gonna have to keep copy pasting and changing the people's name? Person 2, their favorite number will be 3. We'll name them Allie. Person 3, their favorite number will be 7. Their name will be Chad or something. Oops. This obviously isn't a great way to create lists and large number of peoples because we have to statically keep typing them in. So a much better way to create a list, and let's actually just go ahead and delete Patrick too. A much better way to create a list is to use a data structure called an array. An array is a way to store a list or a sequence of objects. Creating an array works the exact same we've seen to initialize other different types. Typically, we do the type of the object, the visibility of the object, and then the variable name. We do the exact same thing with arrays. We'll say we want a people array. These little brackets represent that we want an array of people. We'll give it a visibility of public, and we'll call it people. You could do the same thing with uint256, for example. You could say uint256 public favorite numbers list and just add this little array key here. And now favorite numbers list is going to be an array or a list. We're going to comment that out for now. Now, if I were to go ahead and deploy this contract, let's go ahead and delete the last one. Let's redeploy. We now have this blue people button here. Remember, since it's public and it's a variable, it automatically is given a view function. It's given one of these blue buttons. And instead of just having it be a single button where the value shows up, it's giving us a form to fill out. It wants to take a uint256 as an input parameter. So if I put 0, I get nothing back. If I put 1, I get nothing back. No matter what you put in this box right now, we're going to get nothing back. This is because our people array or our people list is currently empty. And the value that it wants is going to be the index of the object that you want. So for example, if at index 0, I had Patrick, it would show Patrick for 0. If at index 1, I had John, or actually better yet, 2 Patrick, 7 John, etc. This is what it would show. But since it's empty, it's going to show nothing. And let's go ahead and remove the public variable from favorite number so that we don't get the duplicate functions at the moment. we'll just get the retrieve function. We'll show you how to add to this array in just a second. This type of array is what's known as a dynamic array because the size of the array isn't given at the array initialization. If we were to say a people array and add a 3 in these brackets here, that means that this list or this array of people could only be 3 people big. If we don't give it a size, it means it can be any size, and the size of the array can grow and shrink as we add and subtract people. If I add 3, it can only have a maximum of 3 in the array ever. We're going to work with a dynamic array because we're going to want to add an arbitrary number of people to this array. So let's go ahead and create a function that's going to add people to our people array. So we're going to say function add person, and we're going to take string memory name as input parameter, and I'll explain that in a minute, and a uint256 underscore favorite number. We're going to make this a public function. What we're going to do is we're going to call a push function that's available on our people object. So we're going to say people.push, and we're going to create a new person, a new people object, which is going to take in the favorite number and the name. Now, this might be a little bit tricky to you, so let's break this down. People here is capitalized. So we know that since it's capitalized, it's referring to this struct people and not our variable people. The lowercase people here is referring to this lowercase array. So we're saying our array.push, or push is the equivalent of adding basically, a new people that grabs favorite number and name. Another way that we could actually do this is we could create a variable of type people and then add it like so. So we could say people new person equals people, and then we could put those brackets the same way we did before. We say favorite number is going to be this input value, this parameter, and we could say name is going to be this parameter. Now, if you hit save, you'll get this error set here saying data location must be storage, memory, or call data for variable, but no one's given. For now, we're just going to add the memory keyword here, and I'll explain what it does in a little bit. And then, of course, we need to add the new person into our people.push right here. So this is how we're actually going to push people into our people array. And I'll get to this memory keyword in a bit. Now, if we go back to our deploy tab, we delete our last contract. Let's deploy this new one. Right now, if we try to look at the 0th person in our people array, we get nothing. But let's go ahead and add a person. We'll call it Patrick will be the name, and 7 will be the favorite number. So we added Patrick, we added 7. Now if we look at people 0, we should see the 0th person has a name of Patrick and a favorite number of 7. Boom, and that's exactly what we do see. We see a favorite number of 7, and we see a string name Patrick. We tried to add John and do a 16, and we hit add person. We can see our transaction go through. And now if we go to people at 0, it's still Patrick with a favorite number of 7. But if we look at the people at index 1, it's going to be John with a favorite number of 16. And if we look at 2, this of course should be blank. And we do indeed see nothing actually happens here. Perfect. Now there's actually a couple of different ways to create this new person here. Like we showed before, we can use this bracket notation, or what we can do is we can actually just add the parameters in the order that they show. So the first parameter for people is going to be favorite number. So we could just do favorite number, comma, and the second one is going to be name. And the second one is going to be name. So if we save this line we just created is the exact same as the last line. We're being a little bit less explicit here. So the other way is generally a little bit better because it's more explicit as to what variables are what. Or we don't even need to save to this variable here. We could take out this whole line, replace new person with exactly what we just saw, like so. And now we don't even need the memory keyword. Now you've probably seen this by now, but if I go ahead and compile and I see a little red 1 here, and I roll over it and it says something about an error, expected semicolon, but got bracket, all these errors mean that your code isn't compiling. It's not working as expected. So now I can go over here and do a little semicolon, recompile, and I get a green. Now, if I delete this top line, for example, and I compile it, I actually get a yellow thing. Yellow stands for warnings. The warning that I get is warning, SPX license identifier not provided. you should add it. So let's go ahead and add that back. I recompile and the warning goes away. Warnings don't stop your code from compiling. So if you get warnings, it's okay. But it's usually a good idea to listen to the warnings because often they'll give really insightful information about how to improve your smart contracts. So to summarize, if it's red, it's broken. If it's yellow, you might want to check it out, but it won't stop you from continuing to code. So one thing that you'll notice here is that we have this memory keyword. And you'll notice if you try to delete it from our function here, and you try to compile, you actually run into an error. Data location must be memory or call data for parameter in function. Now, there are actually 6 places you can store data in Solidity. You have the stack, memory, storage, call data, code, and logs. We're not going to go over these right now, but we are going to focus on 3 of the big ones, or 3 of the important ones for this section, which are call data, memory, and storage. So for this section, we're going to talk about call data, memory, and storage. And this is a little bit advanced. So if you don't totally grasp it the first time, that's totally okay. Please continue, even if it's not crystal clear what's going on here. Call data and memory mean that the variable is only going to exist temporarily. So this name variable only exists temporarily during the transaction that this add person function is called. Storage variables exist even outside of just the function executing. Even though we didn't specify it up above, our favorite number is automatically cast to be a storage variable, since it's not explicitly defined in one of these functions. Since we don't need this name variable anymore after this function runs, we can keep it as memory, or we could keep it as call data. You can have a parameter as call data if you don't end up modifying the name. For example, we couldn't reassign name to equal cat here. If we compile, we run into an error. Type literal string cat is not implicitly convertible to expect to type string call data. However, if we have this as memory and we compile and save it, that error goes away. Call data is temporary variables that can't be modified. Memory is temporary variables that can be modified. And storage is permanent variables that can be modified. Now, even though I just said there's actually 6 places where we can access and store information, we cannot say a variable is stack, code, or logs. We can only say memory, storage, or call data. You'll learn why in a much later section. Now, this is a bit of an oversimplification of this, but that's essentially what's going on. The next question you might have is, well, why do I need to say memory here, but I don't need to say memory here? Well, let's go ahead, put memory here, and hit Control S or compile, and let's see what happens. We get from Solidity, data location can only be specified for an array, struct, or mapping types, but memory was given. Arrays, structs, and mappings are considered special types in Solidity. Solidity automatically knows where a uint256 is going to be. Solidity knows that for this function, a uint256 is going to live just in memory. However, it's not sure what a string is going to be. Strings are actually kind of complicated. Behind the scenes, a string is actually an array of bytes. And since a string is an array, we need to add this memory bit to it because we need to tell Solidity the data location of arrays, structs, or mappings. And a string is secretly an array. So that's why we need to tell it it's in memory. You'll notice we can't add the storage keyword here. Solidity also knows that since this is a function, this name variable isn't actually getting stored anywhere. So it says, hey, you can't have that. You need to have it be memory or call data. And those are the only 2 that it accepts. So this is what we want our function to look like here. So the summary of this is structs, mappings, and arrays need to be given this memory or call data keyword when adding them as a parameter to different functions. We'll learn more about storage, memory, and call data in later sessions. Now, this list is great, but what if we know someone's name, but we don't know their favorite number? Well, what we could do is we could look through the whole array looking for that person. For example, in our contract, we could say, okay, I'm looking for John. Okay, let's start with 0. No, okay, that's Patrick. Okay, let's go to 1. Ah, okay, that's John. Oh, great, his favorite number is 16. Well, this was really easy because we only had 2 people. But what if we had hundreds of people in this array? Well, we'd have to iterating all the way up to the index that that person was in. It's obviously really inefficient. What's another way to store this information so that it's much easier and quicker to access? Well, another data structure that we can use is something called a mapping. You can think of a mapping as sort of like a dictionary. It's a set of keys, which each key returning a certain value associated with that key. And we create a mapping variable the exact same way we create all of our other variables. So this is going to be a type mapping of string to uint256. This is going to be our type. Our visibility keyword is going to be public, and we'll call it name to favorite number. And now we have a dictionary where every single name is going to map to a specific number. So let's add some capability to our add person function. So we are going to add our people to our array, but let's also add them to our mapping here. What we'll do is we'll say name to favorite number at key name is going to equal to the favorite number. So let's go ahead, compile this. We'll go to our deploy screen. We'll deploy this. We'll click. We have a new button named a favorite number. If I type in Patrick, nothing shows up. If I type in Patrick, you'll see I get a 0 response. If I type in John, I also get a 0 response. If I type in Becca, I also get a 0 response. When you create a mapping, you initialize everything to its null value. Every single possible string on the planet right now is initialized to having a favorite number of 0. So if we want to change that, we'll have to go in and manually add that. So let's go ahead and add a person to our mapping here. So we'll add Patrick, and we'll say my favorite number is 7. And it looks like that transaction did go through. We'll also add Becca, and we'll say her favorite number is 13. We'll add John, and we'll say his favorite number is 16. Now, if I look up Patrick, I'll immediately get back what Patrick's favorite number is. I get 7 back. If we look up John, we immediately get back 16. Becca, we immediately get back 13. And we also can see them in our array because we kept in this people.pushbit. So at 0, we see Patrick's there. At 1, we see Becca. And at 2, we see John. In our mapping, we're saying the string name is being mapped to the uint256 favorite number. And a lot of my variables, I like to make them explicitly named like that. So this is name to favorite number. So now we're in a space where let's say that we really like our simple storage contract right now. We have a favorite number global variable that we can save a favorite number to with our store function. We have a mapping of name to favorite numbers, and we have an array of a new type that we created called people. We can add to both the array and to the mapping using this add person function that we've created. We're able to save multiple people's favorite numbers as well as kind of a global favorite number as well. Let's say we really love this contract and we're ready to send it to a test net to have other people interact with it. Now, in future sections, you'll hear me say that you shouldn't do this until you write tests and until you do some really simple auditing. But for now, let's go ahead and learn how to actually deploy this to a test net or to a real network. Now, remember, test nets are run out of the goodness of people's hearts. So if it's a little bit funky or maybe it doesn't work exactly as we show here, that's okay. As long as it works with the JavaScript VM, you'll be all set. But it is good practice to learn how to deploy these to a real test net. Let's go ahead and do that. Our contract is here, simplestorage.sol. It's compiled. Compiling is passing. We get this little green check mark here. We go to the deploy section. Let's go ahead and delete this. And now we're going to change the environment. So we were working with a JavaScript VM or kind of this fake simulated environment. We want to now move to either injected Web3 or Web3 provider. If you hover over injected Web3, there's this really, really small text here, but this basically means we're going to inject our MetaMask or our Web3 wallet into our browser to use, similar to what we did with the faucet. We'll pick our account we want to use. So I'm going to go ahead and pick account 1. And now we actually see our account in the account section of Remix. Injected Web3 means we're using our MetaMask or whatever Web3 wallet. Web3 provider is when we a little bit more manually choose an endpoint, and we're not going to go over this right now, but as we get later into the course, you'll understand what this means. So we're picking injected Web3. Whatever network our injected Web3, or in this case, our wallet is connected to, is going to be the network that we deploy to. So for this section, we're going to be deploying to Rinkeby. But again, depending on whatever the recommended testnet and the recommended faucet is, that will dictate which testnet you should actually deploy to. For us, it's going to be Rinkeby. To deploy to a testnet, remember, we're going to need gas. So we're going to need some test Ethereum, or if you're deploying to a mainnet, main Ethereum, which you shouldn't be, come to the top of the GitHub repo to make sure you have the most update faucet. The other place you can go is link token contracts page in the Chainlink documentation and scroll down to Rinkeby, and you can see testnet link available here, testnet ETH available here. So this is the other location you can always look to find the most up-to-date faucets. And both of them point right back here. So now that we're working with injected Web3, we can just go through the exact same steps to deploy to a testnet as to deploy to a virtual machine. And remember, if you run out of gas to deploy this, be sure to check back to the faucets to actually deploy this. So we're going to do the same thing. We're going to go ahead and hit deploy, but this time MetaMask is going to pop up and ask us if we want to actually deploy this. This is the exact same as what we saw with the blockchain example, where we sign transactions. We are signing and sending this transaction. The data of this transaction is this massive data thing here, which represents the contract that we just created. We can see all the payment information for this transaction for deploying this contract. We see it's going to cost around this much Ethereum to deploy. But again, we're on the Rinkeby test network, so this is going to be fake Ethereum. We're going to go ahead, hit confirm. And if you pop up the little console in Remix, you'll see that after a slight delay, it'll actually say, have this green check mark that it's confirmed and that it actually went through. We can go ahead, right click, open a new tab, and view this on Etherscan. And after a slight delay, we'll actually be able to see the transaction details here exactly the same as our transaction details for sending Ethereum. We have a hash, we have a status, we have block confirmations, we have timestamp, from, which is going to be us, to, which is going to be the address of the contract that we just created. We didn't send any value with this, so this is going to be 0 Ether. And then, of course, we see the transaction fee, and as well as the gas price. Because again, deploying a contract to the blockchain is modifying the state of the blockchain, so we have to pay gas, and we can see all the different pieces here. As we can see, gas limit and gas usage is much higher than just sending Ethereum, since we are putting a lot of data on chain and adding a lot of computation. So this number is much higher than the 21,000 number of just sending Ethereum. Now, if we come back to our remix and scroll down, we're able to see our simple storage contract at this address. If we hit this copy button and we go to the Rinkeby Etherscan and we paste it in the search bar, we will get the contract that we just deployed. And we see this first transaction is going to be the contract creation transaction. So this contract that we just created, one transaction, which is contract created. So now that we have this contract created, we have all the exact same functions that we saw when working with the JavaScript virtual machine, or our fake environment, or our super fake environment. Now we can do all the exact same things that we did with the JavaScript VM, but on a real test network. So you'll see if I hit retrieve, MetaMask doesn't pop up because again, this is a blue view function. If we look people at 0, this is also a view function and nothing pops up. Named favorite number should be blank. So if I type in Patrick now, absolutely nothing happens, right? I get 0 returned because mappings initialize every single key with a blank or a null value, which for Unit 256 is 0. Now, we can go ahead and store a favorite number. Storing a favorite number is going to modify the blockchain, so our MetaMask should pop up for us to confirm the transaction and sign that transaction to modify the blockchain state. So I'm going to store my favorite number of 16. We'll hit store. MetaMask will pop up, and we're going to go ahead and actually confirm this. Hitting confirm is equivalent to us signing this transaction and sending it to the blockchain to modify the state. So we're going to go ahead and confirm this. We should be able to view this on Etherscan. And again, it might take a little bit for it to actually index or actually start working. So please be patient with these testnets. And again, this is why when building your applications, you want the testnet piece to absolutely try to be your last step, because you have to wait a really long time and it puts a burden on these people running these testnets who are running it out of the goodness of their hearts. So please try to make this the last step of your actual building process. For us learning right here, it's okay. And after a slight delay, once we hit refresh, it looks like it's indexing on Etherscan. The Etherscan website is still figuring out where this transaction is, According to Remix, it looks like on the blockchain, this has actually already gone through. So now if we hit retrieve, we do indeed see our favorite number is 16. Of course, these two are still going to be blank. And it looks like that transaction has gone through and Etherscan has indexed it. So now let's go ahead and add a person. We'll add Patrick. And my favorite number is going to be 16. We'll go ahead and add person. Again, since these are orange, a transaction is going to pop up because we're modifying the blockchain state. We'll go ahead and hit confirm. And we're going to be a little bit patient here and wait for this transaction to go through. And we should see this update and this update. Now, if I hit name to favorite number of Patrick, I get 16. And if I hit people of 0, I get favorite number 16, and the name is Patrick. Awesome. So you've actually successfully deployed a contract to an actual testnet and actually seen on Etherscan what these transactions look like. You should be incredibly proud of yourself. Be sure to give yourself a high five, a pat on the back, send a tweet saying exactly how excited you are, but make sure to celebrate these little wins. Celebrating these little wins will give you the motivation to keep going and really excite you for learning each new thing. So a huge congratulations if you've got this far. You've deployed your first contract to a testnet. Congratulations. Now, if you want to see what it looks like to deploy to a different network, all you need to do in your MetaMask is switch to a different testnet. See, if we switch to Coven, Remix automatically updates and says, the injected Web3 is now the Coven test network. We could switch again, maybe to Gorelli. We say, the injected Web3 is now the Gorelli. This is the testnet that we'd be deploying to. Of course, we need actual testnet Ethereum to do any deploying, so we wouldn't be able to here. And if we go ahead and hit deploy right now, MetaMask pops up, but we get this little red thing saying insufficient funds, of course. Later on, we'll learn how to add new networks like Polygon, like Avalanche, like Phantom into our MetaMask so we can deploy from any one of them as well. Now, I mentioned this term before, but all this code that we wrote, when we hit this compile button, it compiles it down to the EVM, or the Ethereum Virtual Machine. Don't worry too much about what this means. The EVM is a standard of how to deploy smart contracts to Ethereum-like blockchains. And any blockchain that implements a type of EVM, you can deploy Solidity code to. Some examples of EVM-compatible blockchains are going to be Avalanche, Phantom, and Polygon. Since these are EVM compatible, this means we can write our Solidity code and deploy to these blockchains, which again, I'll show you later on how to add these new networks into your MetaMask and then how to deploy them. Let's do a quick recap of our first smart contract, and then you should absolutely take a break, maybe get some ice cream or a coffee, because you absolutely deserve it. Congratulations. The first thing you always need to do in your smart contracts is tell Solidity what version of Solidity that you're going to be using. And additionally, you want to add an SPDX license identifier. Then you have to create your contract object and name your contract. A contract in Solidity is similar to a class in other programming languages, and everything inside the squiggly brackets is a part of that contract. There are many different types in Solidity, like unsigned integer 256, Boolean, string, bytes 32, etc. If we want to create a new type, we can create what's called a struct in Solidity. You can create arrays or lists in Solidity. You can create dictionaries or what's called mappings in Solidity, or hash tables, which when you give it a key, it'll spit out the value that that key represents. We can create functions in Solidity that modify the state of the blockchain. We can also create functions in Solidity that don't modify the state of the blockchain. View and pure functions don't modify the state of a blockchain. We also can specify different data locations in our functions. Call data and memory mean that that data is only temporary and will only exist for the duration of the function. Storage variables are permanent and stay there forever. Function parameters can't be storage variables because they're only going to exist for the duration of the function.